Hello everyone, welcome to Academic Coordinates. In this video, I'll be deriving the Navies-Stokes equation. This is a very famous equation in fluid mechanics, and it is used to describe flow for incompressible fluids. Now, those are fluids with a constant density. Before us, we've got the Navies-Stokes equation. Let me just initially describe its components. We've got P, this cute little P. This one is density, which is different from this one. This one is pressure. What else do we have? We've got this guy over here. This is velocity. We've got this. This is the body force field. And we've got this. This here is viscosity. Okay, to derive this equation, we are going to start from the Cauchy's equation of motion and then move from there, right? So from Cauchy's equation of motion. Okay. So we've got the density, the material derivative. This equals to this over here plus del dot the stress dyadic. So this over here is the stress dyadic, or you can just say the shear stress dyadic. Okay, so we are going to start with the left hand side and break it down to a point whereby we're going to reach the portion of the Navies-Stokes equation that we have over here, right? So this remains the same, plus we are going to express the stress dyadic in a different form. So it's going to be minus P, the item dyadic, plus 2 multiplied by the viscosity. Then that's the deformation rate dyadic, plus 1 lambda del dot V. Okay, so at this point in time, we are going to break down the deformation rate dyadic. So we've got this plus 2 multiplied by the viscosity, then times 1 over 2 del over here V plus the transpose of this guy over here. Okay. Obviously plus the item dyadic lambda del dot V. Okay. Let us simplify that. We are deriving the Navies-Stokes equation. So, okay, let me take it stepwise. Minus P plus. So if I multiply it by 2 times viscosity, this portion, we are going to get this plus the transpose over here, then plus the item dyadic lambda del dot V. All right, so now we are going to dot everything inside the brackets, all right? Then minus now, so del dot the item dyadic, we're going to get the vector back. So at this point, we're going to have minus del P. Then this P is the pressure, right? And then we are going to dot del over here with this portion. Plus transpose. Trust you guys are following. Plus del dot the item dyadic lambda del dot v. Okay, guys. So from here, I trust that you guys are following. So this still remains the same, minus del p plus. All right, so it's going to be del dot the viscosity del v plus del dot the viscosity times the transpose portion over here plus, okay, so del dot the item dyadic, we're going to get the vector, so it's this dot lambda del dot v. Okay, then we continue further. So minus del p over here, then plus del dot this portion, viscosity del v plus. So we are going to dot this viscosity here and this portion of the transpose. So del viscosity, we are going to get this term okay, and then obviously we're gonna do the same even for this portion over here. I think I'm running out of space. Now write it underneath here, plus del lambda del dot v plus lambda del into del dot v. Okay, so now we are going to use identities to actually transform certain portions of our equation, right? So if we can look at this portion, we're going to transform this portion and this portion over here using the identities for dyadic. This is the density times the body force field minus del P plus del into, okay. So when we actually use the identities, this is what is going to result. Let me actually write this in a different color. So this portion over here will be del v dot transpose plus the viscosity here del into del dot v. Then the green portion, just going to write it here, you know. squeeze it here. As you guys can see now that the identities for dyadic are assisting us over here in terms of, eliminating all the other aspects. The aspects of transpose, So if you guys can see that, you would appreciate that we don't have any portions where we have transpose. So these identities are making our lives much more simpler, and I'm sure that you will be given in class the manner in which you guys can do this. Okay, so at this point in time, I want to draw your attention, guys, to something. Okay, let me just continue here. The density times the body force field minus this over here. And then this will not change. LV. All right, so we are going to factor out the viscosity and lambda. If you guys can see, we have got, okay, plus this portion is going to remain the same, dot this. So if you guys can see over here, we have got lambda, sorry, we've got the viscosity and lambda over here. So what we are going to do is that we're going to factor these two out. Let me actually write it in another column. Plus the viscosity plus lambda into what? Into, I like brackets, del to del dot V over here. That's not such a good handwriting. Plus this portion over here. Okay, so I think let me write that neatly now. And then we are going to simplify it further using the Stokes' hypothesis. Del V plus del V dot del viscosity plus, I trust you guys can see the factored out part. Plus lambda there. Okay, so at this point in time, guys, we are going to use Stokes' hypothesis, which states that lambda actually shows the relationship between lambda and viscosity. So it's minus 2/3 viscosity. So basically, we need to actually look into our equation and see as to where do we see lambda and viscosity. Wherever there is lambda, we're going to put it in this way, Okay, cool. This is, okay, let me just continue with this ping. Minus P plus lambda delta V. This stuff remains the same. I think I should have continued with my white plus. Okay, so at this point in time, guys, wherever we see lambda, we need to replace it with negative 2/3 multiplied by the viscosity. So here is the viscosity minus 2/3 into this Okay, plus, right, it's actually going to be a minus over here. This is minus 2 over 3 in this portion. Okay guys, so we're going to simplify this further in this case. So we've got del that is our this over here, then into del dot v. Okay, so I trust you guys can see that we, wherever there was lambda, we substituted negative 2 over 3. So there is that, you know, for this portion. Okay guys, we are getting there. Let's just simplify further. So this is p fb minus plus, okay, oh no, dot plus, so 3 over 3 minus 2 over 3, that is going to be 1 over 3 times lambda to del dot v over here minus 2 over 3 then lambda. Look, I actually place square brackets over here. Okay guys, so at this point in time, remember that we are dealing with incompressible flow, right? Let me actually get another color for that. And actually state as to how does that apply to what we are doing here. So, number one, for incompressible flow, the density is constant. That implies that del dot v is 0. And secondly, for Newtonian fluids, we have got a constant viscosity, right? Okay, so how does that help us now? Our equation is going to shrink to a certain degree. So this part is going to be 0. This part as well, you know. And then we continue from there. Okay, so also if we look here, okay, let me just write it down. So our equation will be, this is the left hand side, remember, FB minus P over here plus del dot this portion delta V. Okay, so if you guys can, you know, look here, this portion is going to be 0 as well. So this is what we are left with. And then the reason that these portions are being simplified to 0 is because we are dealing with an incompressible fluid, and hence del dot V is 0. And for Newtonian fluids, we've got constant viscosity. So with that being said, this portion of the equation is going to simplify to this minus del dot p plus, so we're going to use the identities again here. Going to use the identities to actually get here. Okay, I trust that you guys can see this portion, the right hand side, from the portion that we've already covered. So if you look at the right hand side, it actually corresponds to what we have here. Then the left hand side now is quite easy. The left hand side is quite easy. Okay, so this is the right hand side. So for the left hand side, it's actually going to be and I can do this even in one step. The material derivative, we're going to express it in this form, plus v dot del v, and then we're going to use one of the identities. Let me check. We're going to use identity number 12. So with identity number 12, for this portion, the partial derivative here stays the same. So this portion is going to be transformed to del v over here. Okay, and then as you guys can see, that this simplifies to what we have. So basically, the Navies-Stokes equation derived, it's according to what we have on the top there. It's this. Plus this. Okay, and then equaling the right hand side, which is body force field minus this u squared. Okay guys, I think that's about it. So I want you guys to let me know where I might have potentially made mistakes. I think everything is correct. Let me see something. Okay, so this is dot here. That is actually important. Okay, so I think that's that.